Perfect, thanks. Yeah, so I'm here to talk about this, which is my second piece of work on contrails. So, but I think there's some things in there to take away about working with weather data and the kind of importance of like tailoring the data that you're putting into your models to suit the application that you're applying it to. So contrails that I hope you recognize are these clouds that are generated by aviation and are a part of the human impact on the weather and on the climate, and they've got their own radiative effect. So they interact with visible radiation. They're reflecting solar radiation back into space, which is a cooling effect, but then they've also got this warming effect, which is like a blanketing. It's essentially like a greenhouse gas effect. And these two different effects balance, but because the sun only shines during the day, it winds up being a net warming. And sort of in the context of aviation, this net warming is pretty big. It's actually more, although also being more uncertain, it's more than the effect of CO2. So sort of just to underline that, that's all the CO2 from aviation and just the contrails that are existing at this moment. So it's a pretty big effect. So that inspires some amount of interest in it. And we want to be able to model these contrails so that we're able to, for example, do an impact assessment of an individual flight. So luckily, doing some aerosol science that I've borrowed from Joel, we can work out some fairly straightforward conditions for contrail formation and persistence and determine their effect. So we've got this exhaust out the back of an engine, which then goes on to form droplets as the air mixes and cools. And that gives us a first condition for the formation of contrails, which is essentially that we hit liquid water supersaturation during this mixing stage. But then those droplets continue to cool further. They rapidly freeze at the kind of temperatures that planes fly. And then those crystals go on to persist in some cases, like that photo that we saw early on. And that's where they begin to have the real important radiative effect. So in order to model contrail persistence, we also need to be able to resolve this ice supersaturation threshold as well. So those are our sort of two conditions for persistent contrails: liquid supersaturation during mixing and ice supersaturation in the ambient air. So can we model contrails, I suppose, is the next question that comes on. And in order to do that, we need accurate model data that matches the observations that we have so that we've got the spatial coverage that you need to do the modeling. So let's look at the two different parts of that contrail persistence criteria that we determined. So for formation, it's fairly straightforward. When we compare the relative humidity to liquid water, things line up reasonably well. And we can apply this threshold, and it works to model whether a transient contrail or a contrail is going to form at all during the mixing phase. But when we look at contrail persistence, the picture looks quite different, and there seem to be some problems with this data, trying to get the observations to match the model output. And essentially, we're missing these high relative humidity to ice values in the data. But also, it's just poor case-by-case agreement. And that's really going to get in the way of us modeling the impact of an individual flight. So assessing the impact of a particular flight to be able to, ascribe some climate impact to it. So what do we take away from this? Just that relative humidity to ice is a mess and we can't model persistent contrails. That sort of begins to motivate this piece of work that I've done, I guess. So what I've been doing is looking at the weather data and trying to establish a link between where the weather data is going wrong for contrail modeling and the underlying weather models. So when we look at it, it doesn't look like relative humidity to ice is a mess. This is what the purple and the blue field is relative humidity to ice. And you can tell that it's sort of structured in the weather data, in the weather systems that form in this part of the North Atlantic. And that sort of leads to the aims, I guess, which are to identify how this structure shapes the occurrence of ice supersaturation and then relate those structures to the model biases. So to kick off, we want to identify the ice supersaturated regions. So we bang a threshold in at 100% relative humidity to ice in the models. And that gives us these sort of contours that you get there, but also we're motivated by the lacking of high ice supersaturated values, and we set a lower threshold as well. So this 97.97 threshold is the threshold that we reach if we want to match the occurrence rate of ice supersaturation. So that's kind of what we call a humidity correction threshold. Finally, the final threshold we apply is this kind of relaxed threshold, which is motivated by seeing this structure. You see the sort of filaments of humidity. So we just want to see what the impact is on the model biases and accuracy if we really relax this threshold and identify as many supersaturated regions as possible. And then the final part of this work, I guess, in the methodology is to identify the structure. So in the North Atlantic, in the extratropics, the weather is really shaped by these extratropical depressions, these storms, and those are sort of characterized by these surface pressure minima. So those are where we've drawn these regions around it, and we collect the data on the ice supersaturation occurrence within those regions and stack them all together. And that leads us to a composite supersaturated region around a composite storm system, if you like. So you can clearly see that there's structure to the ice supersaturation occurrence rate around these weather systems, and in particular, even averaged over so many systems, you get a dry zone and a more humid band coming up the side. So we isolate the signal due to the weather system without any of the sort of background. And this is what we get. We get the dry and the humid. And these parts of the system are called the warm conveyor, which is this ascending air from the bottom of the atmosphere, and the dry intrusion, which is where air that's sort of lingering at the top of the troposphere descends into the system from above. So what we're really interested in is how well those model structures, which are really well easily identifiable, are capture the observed state, the true state of the atmosphere. And when we composite the observations in exactly the same way, they're much more sparse, but you still see the same kind of structure, which is good because it basically means that the model's not hallucinating anything. But that doesn't really answer this question that we want to answer, which is what is the impact of the individual flights? How well do the models capture the behavior of the individual flights, and where do the biases sort of come into play and as they're related to the processes that build up in these systems? So what we do is we calculate these performance metrics, the precision and the recall on sort of an individual measurement basis. So the precision kind of tells us something about the confidence in the diagnosed population of ice supersaturated regions, and the recall tells us sort of the comprehensiveness, how many of the ice supersaturated regions that we observe when we go and look for them do we actually see. So this is what we get. So just to set the context for these figures, we've got the different parts of the system, the warm conveyor, that ascending air, the dry intrusion, which is that descending air, and then just all the points in the system, as well as the different scalings, those different sets of supersaturated regions that we diagnosed on that map that we saw. And you pick out some different conclusions from different parts of this. So to begin with, the performance is just markedly worse in the dry intrusion, and this speaks to some kind of systematic errors in the weather forecast model. So that's sort of what we'd expect from the messiness in that distribution that we saw. But as well as this precision generally being bad, it's worse in the dry intrusion. There's some sort of systematic process errors that need correcting, and the model needs constraining better in order to be able to correct this. You can't just fix it by scaling. The culprit for this, we suspect, is this descending air. It comes from a part of the system that is poorly resolved, and more work can be done to be able to resolve that better by making observations in the upper troposphere, the upper tropospheric humidity, maybe. The other thing we see is that this correction, this matching the occurrence rate, doesn't boost the confidence on the individual supersaturated region level, which is kind of a weird thing to think about. but it basically means that we're not correcting for the purposes of measuring individual flights. But what we do see when we scale is a huge increase in the comprehensiveness of the supersaturated regions. We miss far fewer, which means that if you wanted to do something like mitigate the impact of a specific flight, which you do by rerouting, you'd catch more flights that you needed to reroute without that much cost in terms of the precision. So if you're following that, that means that you want to explore recall optimization rather than humidity correction for this particular application of trying to catch the impact from as many flights as possible, because I mean you're not even getting that much you're not even being penalized so heavily for in terms of the precision either. So yeah, that's about it for this piece of work. We get the strong structure to the ice supersaturated regions, and that should be borne in mind when you're trying to work with this data. That the ice supersaturation is related to the underlying weather system. We get that there are systematic errors, so that the weather models need constraining a little bit better to be able to work with them if you want to increase that precision and that confidence and decrease the sort of cost that you get by misidentifying ice supersaturated regions. And finally, scaling past the correction continues these improvements that you get in the comprehensiveness of the results. And this sort of underlines this point where you need to tailor the weather data or whatever input data you're using to optimize for the particular aims that you've got. So, that's me.
Perfectly on time. Do we have any questions? Neil.
Do we just yell or do you want to record?
I think you just yell.
Okay.
I think we've only got one microphone.
Very interesting talk, but the horizontal filaments are really interesting, but I was under the impression that the supersaturation layers could also be quite shallow. And have you looked at the vertical extent? And I guess from the point of view of mapping flights, you sort of have 2,000-foot increments to play with in terms of flight levels.
Yeah, absolutely. They are very shallow. We've got some vertical resolution in these composites that we've got, and we chose a vertical resolution that we think allows you to see the sort of vertical variations in the supersaturated regions, and we've resolved the supersaturated regions in the vertical as well. They suffer from the same kind of biases. You get the same kind of effect of extending the region slightly when you, it's a long way to go back, but I can have a go. You're still kind of extending the regions a little bit into these sort of less well-constrained parts. And that's the interesting thing about using a lower threshold, is that you sort of move out into the parts where the ice supersaturation is less well-constrained while you maintain the weather model knowledge about which regions really are dry with these steep areas of the contour, if you like.
Thank you. Any more questions? So I had a question just about so there's a climate impact, and maybe I missed it at the beginning, but you're trying to resolve these on an individual flight basis. Is that really where it needs to be?
It depends on your application. So if there's interest from in including these in sort of emissions trading schemes and so on, in which case either you need to assume all flights have some kind of contrail impact or have an incrementally more complex model. And if you want to ascribe a specific impact to a specific flight, you need to know whether or not it goes into a nice supersaturated region, which is hard to do. It's hard to do with models because of this limitation on the weather data, but it's also really hard to do with observations. That's the first piece of work I did, was like you can't observe all contrails.
Great. Final questions? Oh, we have one here. Yep. Joe?
I can just shout into the microphone. Really nice talk, thank you. With the models you're using, are these forecast models? Are they reanalysis? What are they?
These are reanalysis models. So it's ERA 5 reanalysis, and we're looking at the upper troposphere, 250 hectopascals in this. Essentially, reanalysis is pretty well aligned with the weather models at this altitude, just because there's not much data to assimilate. All we're assimilating is a few sparse or microwave observations. So the same biases exist in ERA 5 and the forecast models as well, and a couple of different weather models, I think.
Okay, so it would still be applicable to like if you were trying to reroute flights, you could do the same corrections on the forecasts.
Oh yeah, 100%.
Brilliant, thank you.
Great. Thank you very much. The red light has gone, so.
Just swap this.